Welcome to the liver enzyme lab. We've got some livers. They're beautiful. I don't want to spill them on my computer. There we go. Livers. And we've got some other stuff to look at. And no worries, Lane. Yeah, guys, you may notice if you ever try to pop into my virtual session early, right? I might be doing another session that exists, right? I do chemistry right before this. So if you come in too early, then I'm probably going to be talking about electron configuration, which you should know, oh, that was nothing to do with me, right? All right, liver enzyme lab. So what's happening right now is we're going to go through this PowerPoint that I made, and we're going to look at some live action enzyme stuff. Nope. Okay. So we are going to get started here. Liver enzyme lab, taking forever to load. Bonnie, are you watching this from your car? Shout out to Bonnie. Dedication right there. Attending the liver enzyme lab while moving. Okay. Today we're going to model enzymes working in a cell by using an organ filled with many enzymes, specifically the liver, right? We're going to talk about exactly which enzyme we're looking at. We're going to describe the relationship between enzymes and temperature specifically, but we're going to then apply that knowledge to other environments. And then we're really going to also talk about how we can prove that a reaction is happening, which I am not going to be proving the reaction happening today, but I will link you guys to a video where I did prove it previously. Okay. Oh, good. My water's starting to boil. Perfect. So we're going to start off with a warm-up of you filling out the beginning part of the lab. I'm going to paste the link to the lab in the chat. You probably saw this lab already, right? Maybe not. If you haven't, pretend you haven't opened it. Make a copy of your lab so that you have your own physical copy of this, right? A digital copy, I guess I should say. And what we're going to be doing is we're going to be filling out the first part of this lab. You should see there's a bunch of background reading. You're already kind of familiar with enzymes if you've been keeping up with the class. So you should be able to go straight to these pre-lab questions where you may need to use some of the information provided in the first part of the lab, especially when we're talking about a specific enzyme. So I'm going to give you, what do you guys think? You need 3 minutes to do this? Or do we need 1 minute to do this? I think 3 probably. We'll do 3. I'm going to mute myself for 3 minutes. You might need longer, but you're going to get as much done in 3 minutes as you can. So most importantly, you're going to be really caring about questions 1 and 2 is what I mostly want you to focus on answering. The other ones are reviewing material, so they're not quite as important at this moment. 3 minutes right now, questions 1 and 2. I'm going to be setting up the lab as we go through this. All right, if you're just tuning in or you're confused, make sure you are looking at these pre-lab questions. You are attempting to answer questions 1 and 2 at the very least, also moving on to future questions. I'm just grabbing a few other supplies that we will be needing. All right, I'm back. Okay, so we're gonna quickly talk about these questions and we're gonna talk about what I've been doing in the background while you were reading / answering. Make sure you have your video on, right? Unless you have a, unique situation like you're Bonnie and you're in a car where your video might cut in and out, that's fine. But remember our virtual session policies and rules. Okay, so first question, which gas will be released if the enzyme is working? Anybody have an idea for that one? Try not to touch my mouse pad with liver fingers here, but it's gonna happen, I think. Great, we got some people popping oxygen into the chat. That is 100% correct. Where did you find that information? Right, should have been in this formula, very big and bold on the center of the first page here. Also telling us the enzyme's name. So we're gonna be looking at the enzyme catalase. And something you will notice as we go through this class is that enzymes most often end in ACE, A-S-E. If you see ACE, you should immediately think, that's probably an enzyme. Amylase, catalase, peptase. There's a bunch of other ones. Anything with an ACE at the end. Why isn't it ACE? Because that's how you spell enzymes. Yes, Joel, it does. Your camera is still working when you click off the Zoom to take notes. That is perfectly fine. So I don't know, Lane, why it's spelled A-S-E, but that's how it is. Sometimes there are other enzymes that have different names, right? But if you see ACE at the end of a word, chances are it's an enzyme. So then already you should know what it does. Oh, it's building or breaking something. That's easy. In this case, we're looking at catalase, which catalase is written over the arrow because enzymes are not actually part of the reaction. This is a common misconception. People always think, oh, well, the enzyme is getting used in the reaction or the enzyme is part of the reaction. No, the enzyme is facilitating the reaction, right? It's like if you were trying to get 2 of your friends to make up and you bring them together and you say, let's work it out, guys. You're there to support, right? But you're not actually doing any of the making up. That's how enzymes work. So in this case, we don't ever see the enzyme written in the equation. Oh yeah, my computer is gonna die. Thank you. Miss Norander is here and she's helping me not lose this. It is the third wheel. Great way to describe it, right? Although it is unaffected. The enzyme does not feel sad about being the third wheel. That's its job, it's happy. So in this case, we have hydrogen peroxide. Common household item. What does this get used for? Cleaning wounds, cleaning things, right? Type a 1 in the chat if you've ever poured this on a cut and felt the pleasure of hydrogen peroxide cleaning. Oh yeah, I see Alexis getting involved there. Yeah, right? It burns. Well, it's a bubbly thing, so we expect it to be bubbling. Well, guess what? Chicken liver, which looks like this, just looks like a liver. It's brown and bloody, dripping blood on me a little bit. Chicken livers contain a ton ton of catalase. Basically, any organ does. But in this case, what catalase does is it breaks down hydrogen peroxide into water and oxygen. Hydrogen peroxide is a poison, right? Your body is really adept at breaking it down. However, if you don't break it down, you will die, right? Livers are usually involved in detoxing or involved in getting rid of toxins or breaking toxins down. So it makes sense that livers would have a ton of enzyme in them, right? That's also why they're really healthy for you to eat. I personally do not eat them because I have a thing with animal stuff, but some people eat them. So in this case, what we're going to do is we're going to actually see the liver break down this hydrogen peroxide into water and oxygen. So back to our pre-lab questions. First question, a lot of people told us oxygen is what we would see, and you were correct. How can we measure that? Right? Because a lot of you know what hydrogen peroxide looks like. It's clear. How am I going to know that oxygen is being released? Are you just going to believe me? You should all be going, yes, we believe you. But how are we going to prove that? We could measure the oxygen levels in the liver and afterwards. Okay, so maybe that more oxygen would be present in the liver after it's broken down. Maybe. See the difference? How am I going to test that? By just looking at it? Can I see it? Do I need a $5 million tool to do that? Ooh, Elizabeth, love it. Bubbles. If we see bubbles, we know there's a gas, right? Well, we would hope it's oxygen being released here because that's the only gas that's supposed to be released, right? An air gauge thing. These are all good guesses. Well, we will prove because I found the correct supplies in order to prove that oxygen's present. We will do that. That's going to be important to note. Okay, we're going to be studying the liver at 4 different temperatures. What is going to be our control? In fact, while you're thinking about that, I'm going to show you our 4 liver setups. Liver 1 is currently sitting in a lovely hot water, boiling water bath. Right there. It is boiling. So that's one of our temperatures. Another temperature is going to be body temperature, which the way I'm going to get that done is basically I'm going to heat it just a little bit in this hot water until it's pretty close to body temperature. We're going to have a liver piece that's at room temperature, which has just been chilling out in the room all day. And we're going to have a piece of liver at a cold temperature. In this case, it's chilling in some ice. Actually chilling, literally. So would any of those be a control, or would we do something else as our control? What do you guys think? What is the purpose of a control anyways? Elizabeth, I think, is saying, oh, yes, Colin, I almost missed your answer. A chicken liver without anything added to it will be our control. Yeah, that is one way we could do it. We're also going to just pour hydrogen peroxide into a cup and see what it does by itself, right? Because if we're measuring amount of bubbles produced here, well, we want to make sure that the hydrogen peroxide is not just bubbling like crazy on its own, right? Because then maybe the liver's not doing anything. So you're right. We could just look at a piece of liver when it's by itself. It looks gross, but it's just doing nothing. There's no bubbling, right? I don't see any bubbles. Or, right, we can also just look at hydrogen peroxide by itself. We're not going to use any of our temperatures as a control exactly in this experiment, which we'll talk about why in a second. The average body temperature of a chicken is 41 to 45 degrees to have a base. Well, thank you, Lane. I'm going to grab a thermometer, and I forgot that I think I did this when it was colder out and I had a jacket so I could touch my hot glassware. So I'm going to use my little scarfy thing. See if I can get this guy out. Might not be the safest concept here. Might not get it out. All right. So what I want you guys to do right now is predict which temperature you think is going to produce the most oxygen and why. You can just bold one of these choices and then next to it write your reasoning. For body temperature, we're actually gonna probably get a little warmer. Actually, I think chickens are a little warmer than humans in terms of body temperature, so we'll be pretty close to actual chicken body temperature. Boiling, right, is 212 degrees Fahrenheit. Celsius, it is 100. Ice cold, right, we're gonna get it as close to 32 degrees as possible. Again, that would be close to 0 degrees Celsius. And then room temperature, I believe it's about 70 degrees in the room. Celsius, that would be, what, like 22? So make sure you have an explanation and you choose one of those things. I'm gonna grab a thermometer. If you get done with that and you need something else to do, you can start on your setup. Sketching the setup. You haven't seen much so far, but you have seen 4 test tubes filled with liver, so that's something. I'm gonna grab a thermometer and hopefully a thing to grab hot stuff so I don't burn myself. So I'm leaving you guys for about a minute and a half, 2 minutes, predicting, setting up. All right, let's see some predictions in the chat. What are you guys thinking? Which temperature is going to be the most effective at breaking down the hydrogen peroxide and producing oxygen? And of course, with a reason. Body temp, I'm seeing as a thought. Are people agreeing? Ooh, boiling, Colin says. Okay, anybody else have an idea about this? Body temp because it's not too hot or too cold, which would cause denaturation. Oh, I love it, Lane. Lane gets a special shout out for using correct science terminology here. I really need a glove to do this. I'm gonna change my strategy. So in case you guys don't know what I'm doing because I'm off camera right now, I'm about to burn myself. So not on purpose, obviously, but I have a very hot item and I don't have a glove, which I believe we used to have a glove and I don't know where it is. So I'm trying to figure out how best to do this without burning myself and failing. Okay, so we're gonna start with the easier ones that don't require me to have heat. So we're gonna start with our room temperature chicken liver. What we're gonna be doing is measuring the height of the bubbles. Let's see, we got other people chiming in here. The heat will activate the enzymes and the heat will do a lot of melty things. So that's Colin's reasoning, love it. Body temperature because it doesn't have anything to affect it. Okay. Boiling or ice would be like heat stroke or hypothermia. Boiling will be most effective because it is super warm and molecules can move. Good, so I like that you guys are connecting that heat does speed up reactions, right? Or heat does help reactions. So that is a good thing to note, right? And we will find out in a moment if you are, in fact, correct. Yes, I moved off the thing without burning myself. Victories. Okay, so what we're gonna be doing is we're gonna be collecting data on this. The way we're measuring this is height in centimeters of the bubbles produced. And I just realized, wow, I'm like really unprepared today. I don't even have my ruler over here. So I'm gonna have to grab a ruler. While I am, oh, thank you, Mr. Orator. So while we're waiting on this ruler here, I do want to say one final thing about this. The measurement of our oxygen, right, we're going to do height. Is that the most effective way to measure the amount of something, maybe not, right? However, with the tools we have, we are going to be able to sort of estimate, basically, does this one produce more or less bubbles than the other ones, right? So this by far is not the most accurate scientific experiment. In fact, it's pretty hard to create, thank you, an accurate scientific experiment. But in this case, we're going to be just measuring the height. And I can tell you guys from doing this before that it does matter, right? We will see a difference. So it's not like they're all going to be the same. So first step is our control. What happens when we just pour hydrogen peroxide into a beaker by itself, / what happens when we have liver by itself? Do we see any bubbling? Easiest question of the day, and no one answers it. Oh, there we go. Do we see any bubbling? No, the liver's just chilling by itself. What does hydrogen peroxide look like when you pour it by itself? Is it doing anything? No, right? It looks like water. Doesn't smell like water, though. So no, we see nothing. So for our control, what are we going to write for how many height in centimeters bubbles were produced? 0, right? Which is great because now we have a really easy control. Our control was 0, so if we have anything other than that, it's something, right? So we're going to start with our room temp. And I'm also going to be monitoring the temp of the body temperature one. What did I do with this thermometer? Here it is. So all I'm doing right now, guys, is I'm going to place the body temperature liver in my really hot water that was boiling before but isn't boiling now. And I'm going to place a thermometer in there, and we're going to basically wait until the liver is pretty close to body temperature, which is not going to be very long because this thing is pretty hot. All right, so I'm going to be measuring that. I got a lot of stuff to manage while you guys are watching here. So we're going to start with our room temp liver. Now, something I did to help control this experiment is I tried to make all of my liver pieces about the same size, right? Because that will matter. If I have more liver, it's going to react more. So I tried to reduce that. I cut them all, eyeball level of certainty that they're all pretty much the same size. If we were going to do this for a real paper or something that we were publishing, we probably would measure them with mass, right, and have the same exact mass. All right, so what's going to happen now is it's probably going to be getting messy in here. I'm going to reorganize the camera so you guys can see the bubbling, hopefully really well. And I'm going to be near the sink in case I have an overflow. So basically, we know that our tube here in full height is about 12 centimeters. So if we go above the tube, I'm just going to measure up from there. Again, not the most accurate of measuring systems, but it will do. So the other question you guys should be thinking is, well, how much hydrogen peroxide are you going to put, right? Am I just going to pour it in? Yes, but I'm going to do the same amount. I'm going to do 25 milliliters of hydrogen peroxide each time that I pour it into the liver. So here comes our first one. Drum roll. 25 milliliters was actually way too much because I completely overdid the tube, so we're going to make it less. Good thing I have more liver. Backup liver. I did not think about that, the tube actually being a certain size, right? Just plop that liver out. Okay, good thing we're going to do that again. That was a really anticlimactic drum roll. I'm going to do 5 milliliters of hydrogen peroxide this time instead of 25 because I want to be able to actually see the bubbles rise up in the tube. Okay. Redo. All right. This is our room temp liver. Wait, are you kidding me? 5 was still too much? Oh my gosh. Okay. The tiniest amount possible. Let's do like 2. We're gonna make this even smaller, 2 milliliters. Because I have the tiniest test tubes in the world. All right. Anyways, I'm off my game today, guys. It happens. That's fine. Thank you. Besides, I thought some of you guys would be here to help me with the lab, but no one wanted to come in person, I see. All right, 2 milliliters. There we go. Now we can actually see bubbling. Bubbling is occurring. I'm going to measure the height of the bubbles. They are increasing, right? They're coming up to the top of the tube at this point. If you can see the liver itself, you see that it's going crazy with the bubbling right next to the liver. Bubbles are increasing up out of the test tube. Still getting a little higher even. And we're going to call that at 13 centimeters. Now that we have the right amount of milliliters going on, this is going to be much faster and easier. We have Miss Norander measuring out our hydrogen peroxide over here. So for our first one, we are going to write 13 centimeters for, that was room temperature. Liver doesn't smell good when it's working here. Okay, so a lot of us thought maybe room temperature would be the highest, right? I think a few people said that. So good thought. 13, let's see what happens now. Do you guys want to do cold or boiling next? Okay, we got a vote for boiling, 1 vote for cold. So we'll do boiling next. So making sure this glassware is not going to burn me. Check out what the liver looks like after it's been in boiling water. What do you notice about it? Right, in case you forgot, as a reference, this is what it looked like before. Kind of hard to see on this computer camera, but does anyone notice anything about the liver itself? What is happening to it? It looks nasty. Hey, that's a description. Yeah, it kind of does, right? It's yellowish. It looks cooked a little bit. All right, so a lot of us said we thought boiled liver was going to be the best. We got our hydrogen peroxide. What happened? Do you see any bubbles? No. I know some of you are disappointed because you were like, boiled liver is going to be the greatest. So why? Thinking back to that vocab word that Lane used before, what has happened to the enzymes in here? It's too hot, right? The enzymes got denatured, right? And what that means is they literally got deformed so that they can't function anymore. Okay, so boiling liver, we can put a 0. Oh, whoops, I still have all my answers from last year. You guys didn't say something to me about that. I have my chat box covering it. Which, surprisingly, you will see, actually, that last year we did get a tiny bit of bubbling from boiling. So boiling was 0. Okay, we're going to do ice cold next. We've got our liver that has been sitting in the ice. 2 milliliters hydrogen peroxide. What is going to happen? If I don't cover it with my fingers too much. Okay, we've got a little bit of bubbling, right? It doesn't look as crazy as it did for room temperature. And looks like that might be, we'll let it keep rising for a second here before I measure it because it is getting taller. So what does that mean for the liver that's freezing? How come the freezing liver is still able to break down the hydrogen peroxide? Why is it doing that? Lane says maybe it's warmed up, right? It's bubbling a little bit, not as much. So maybe some of the enzymes are still working here, right? Which is what you're supposed to sort of get from this, is that It was cold, but it wasn't so cold. It wasn't frozen. All right, I'm gonna call the bubbles here at 9 centimeters. 9 centimeters for our ice cold liver. So again, pretty close to room temperature, but you'll notice it took a little longer, right? It didn't immediately start bubbling and going crazy, right? It might not have gotten cold enough, that's true. You'll notice I do have the liver in a test tube in the ice, right? I didn't put the liver directly on the ice, so that is also possible. So then our final liver here is our body temp liver, which a lot of us predicted would be the greatest, right, in terms of bubbling, which we may see or we may not see. Theoretically, you guys were correct, the ones that said body temperature, right? Because livers are in a body, they should function the best at body temperature. However, you may have seen from my results last year, that didn't happen last year, right? In fact, this liver looks like it might have got a little bit too hot. Hard to control for exactly body temperature, but we shall see. Yep, it got too hot. Barely any bubbles. So this one, it looks like there's the tiniest little layer of bubbles right on the top. So we'll go ahead and call that 1 centimeter because it's a little less, but we'll round up here. Which again, why did that happen? Because this liver got a little too hot. I can see that it's already been cooked slightly, right? I only put it in the hot water for, I don't know, maybe about 3 or 4 minutes, but that was a little bit too long. So we can try again with the body temp, but we're gonna move on to actually talking about how to prove this, because that's my favorite part. And I'm gonna see if I can get another piece of liver here closer to actual body temperature. So we can try that one more time at the very end. So let me get rid of this gross liver out of this one, which is not coming out. Effective method here, it's called dump the liver into the sink. Fun one. I'm gonna have to clean it out, obviously. All right, so I'm gonna let this liver get a little bit warm over here and see if we can try that body temp one more time. Because as you notice, not everything works out perfectly in an experiment, right? Sometimes we know something should happen and it doesn't. So now let's get back to proving. Okay, we're gonna be proving this using some fire. What's the relationship between fire and oxygen? Fires need oxygen, right? When a fire gets oxygen, it fuels it. So what I'm going to do is I'm going to take a giant piece of liver, like almost a whole one, put some hydrogen peroxide on it, not a specific amount, I'm just going to pour a bunch. It's going to start bubbling, right? And we know that oxygen's being released, or we think it is. So I'm going to get an ember on a stick. I should be able to place my ember over my oxygen and it should ignite. I have about a 92% success rate with this, so we'll see how it goes. But I should be able to prove right now that oxygen is being released from this reaction. Hardest part is getting these sticks to make an ember. You have to be very gentle. Okay, we got a little ember. Nope, the ember's still there. Okay, gotta try again. So I'm saying there's a 92% success rate. I might have to try a few times before I get it. But the good news is the reaction's just gonna keep going on and on and on. Oh, I could see a little spark there. We'll see if we can get it a little bit better. It should completely reignite, which these sticks might not. I usually like to use the Starbucks wooden sticks personally because they, oddly enough, make really good embers. There we go. Got a tiny little ember. Nope. Oh, there we go. So the stick actually relit on fire. Ember. It relit. Right, and I could just keep doing this all day because there's going to be oxygen getting released, which will just keep relighting the stick. So this is a way that I could prove that oxygen is present, right? Because if I just hold the ember outside of the reaction by itself, it's not going to do anything. Were you guys able to see that on the video? I don't know if you were able to see it really well. But basically what ends up happening is the ember kind of lights up and then the stick reignites on fire, which is pretty cool. Yeah, the video is really tiny. Actually, you know what? We can make it bigger. I'm gonna have to get a new stick because that one's getting real short. Let's see. I can do this. There we go. Now it's much bigger, right? So we're gonna try this one final time. Notice the reaction is still happening. There's a ton of bubbling going on. I'm just gonna put more hydrogen peroxide. Why am I able to just add more hydrogen peroxide? While I'm getting my ember ready, I'll see if anyone can answer that question. How come I can just keep pouring it in? Well, there's less in the bottle, yeah, but dark magic. Enzymes never get used up, right? They can keep getting reused. Okay, we've got our tiny little fire, which is now an ember. Uh-oh, it's coming back to life. There we go. Ember, smells nice in here. It's hard to like get close enough to the oxygen without putting the ember out. Oh. Which I just ended up doing on that one. Good thing I have a lot of sticks. So this is something that you probably can't try at home, but maybe you could with your parent supervision. You can buy chicken livers at the store. I wish I would have made the video bigger before. There we go. But again, enzymes can get used over and over and over, right? So they will just keep going. Like I could pour this entire bottle of hydrogen peroxide on to this liver and it would be able to break down all of it. It has no limits. It does have limits though if it's the wrong temperature, right? So if the liver is too hot or too cold, then it can't do anything, or it can do less at least. Well, let's try that room temp one more time, and then we're gonna do a little bit of wrapping up and talk about what your next steps are, or not room temp, sorry, body temp. Okay, I've got my body temp liver, which I hope is not overcooked this time. We'll see if it makes a difference. Well, we're getting a little bit more bubbling. Definitely better than the first time, that's good. Right, which is again why if we were doing this experiment to really prove something about enzymes, we would probably do it, I don't know, 1,000 times, right, to confirm things. In this case though, we definitely see that boiling is the worst. Actually, this one's doing pretty good. It's just a little slower to start. I have my centimeters upside down. Try to give it the same opportunity to grow up the ruler. Well, we're gonna call this one at 13 as well. So go ahead and update your body temp to be 13 instead of 1. Because now that it wasn't cooked to death, it actually worked. Okay, so things that you do now with the lab, right? That was the part that you needed me for, was demonstrating with the livers. You are going to be finishing the pre-lab questions. They should just help you make sure you understand enzymes, right? What does it mean to be denatured? Why are the enzymes important? What do all of these vocab words mean? The setup, you can do a hand-drawn sketch or you can do a digital sketch. It doesn't need to be super detailed. Just show me generally what the experiment looked like. The data, you should have all your data written down. And then you're going to work on these data questions, right, as well as the conclusion and analysis questions. Those you're going to do independently. So some of these are kind of hard to do because you weren't here in person. So I'm going to give you a few hints, right? For example, the reaction that lasted the longest might actually have been room temperature. That one went a little bit longer than the body temp one did. But other observations, you guys couldn't necessarily hear the sounds or the smells or the experiences that were happening here. But if you could feel this beaker, especially this huge piece of liver where I did my oxygen proving, it's actually a little bit warm, right? It feels warm because there's a reaction happening. If I listen to it, sounds like Rice Krispies with milk added to them, right? So there's a very crackly, bubbling sound happening, right? So those are two things that tell us that a reaction's happening, the bubbles, right? And the fact that we feel heat. Some reactions you might feel cold or other things like that, right? But in this case, those are two observations that you could definitely make about this reaction that maybe are sort of lost virtually. How did we test for the presence of oxygen? Well, that was with the ember, right? Where I literally put an ember over the reaction and it reignited because the oxygen fueled the fire. So that's a good way to prove that oxygen's being released and it wasn't something else. Otherwise, the rest of these questions you should be able to explain. The one thing I want you to focus on is the actual data numbers. Which one of these sounds better? Option one, I was right. Body temperature was the best. I know at least 5 of you will write that anyways. Option two, body temperature was the best because it produced a 13 centimeter height of bubbles when hydrogen peroxide was added to the liver. And even though it tied with room temperature, right, I know from my studying of enzymes that body temperature would be the best because that is the ideal optimal temperature for an enzyme to function. Which one of those am I going to be giving a higher grade to? Definitely option two, right? So think about that. Use the data, right? Talk to me like I don't know anything about science and I need you to explain what your data means, right? That's going to help prove to yourself that you understand what your data means. And if you sit down and you start saying, I don't know what my data means, well, that's something then that we can work on together. But use the numbers, use the vocab, use the descriptions. Do enzymes die over time? Love this question, right? This is one of the biggest misconceptions too about enzymes, right? Is that you think, oh, they just get used one time, but they can be used forever and ever. Like you have enzymes inside your body that have been there since you were born, right? They don't go away. Of course, you need to get more, right, as you grow in size. So no, they never die. Now, if they get denatured, because let's say that you get a fever of 110 degrees, well, what happens to you if you get a fever that high? You die. You want to know why you die? A large part of that is because your enzymes die, right? They denature, which is sort of like their death. They're still not technically dead because they're not really their own living thing, right? But they are a protein, and when they change shape, that's it. They can't go back. So imagine that you have a Lego that you really like, and your lovely sibling melts your Lego into a puddle of goo. Well, you can't put it back, right? That Lego's gone forever. That's how enzymes are. As soon as they get denatured, that's it. They're done. So they will live forever. The Lego wouldn't be the only thing melted, Colin says. Yeah, right? Hopefully no one in your life is trying to denature your enzymes. I mean, it would be pretty hard to do without killing you, right? But when enzymes get denatured, they don't function. And really, one of the things we're going to start connecting this to is disease, right? We're going to talk about how this shows up. Some people are born with defective enzymes. their enzyme is the wrong shape. It has the wrong active site. It has the wrong whatever. If it doesn't work, right, then they're going to have symptoms of that. For example, we talked about this already briefly, but lactose intolerance, right? Lactose is a sugar. Guess what the enzyme is called that breaks it down? Lactase. Oh, full circle, right? Lactase breaks down lactose. And if you have lactose intolerance, your lactase enzymes are actually inaccurate, right? They're not correctly shaped. They can't break down lactose. So they're there, but they can't do anything. And then as, you know, a result, you end up getting sick when you eat lactose. Now, again, not the worst thing in the world, right? You're going to have an upset stomach. You feel terrible, but you get through it. Other enzymes, if they're messed up, it can be worse. I love this. Joelle says a science villain whose catchphrase is, I will denature your enzymes. Exactly. Yeah, slowly roasting you over fire. So I saw Georgia asked a great question. Hey, I blanked out. What did we use for the control? Who can answer that question for us here? What did we use as a control for Georgia and other people who probably actually weren't paying attention when I talked about the control? Because I know the setup was a little bit askew in the beginning. I don't feel so good, Mr. Liver. Room temp, can you elaborate on that, Lane? Did we use the room temperature liver with the hydrogen peroxide as a control? Did we just use the hydrogen peroxide by itself? Because that's a really great question to ask here. What did we use as our control? And it worries me that no one's jumping in immediately knowing. Okay, so it was two components. First of all, we looked at just hydrogen peroxide when it's poured by itself with nothing. And it didn't do anything, right? It just looked like water. And then we also looked at the liver by itself. Really, we were just looking for, are these things bubbling on their own, right? They're not. They only bubble when they're together. So our control was basically just proving that the liver doesn't bubble by itself and the hydrogen peroxide doesn't bubble by itself. But when they interact, they do bubble. They were organic and GMO free. Yeah, I don't know if these livers are organic livers. I don't even know if you can make a liver organic. Let's see what the packaging says. Nope, it just says Pacific Northwest grown right there. All right, so they're local. We've got one mark. Were they? Yeah. Well, I think they came from actual chickens, I'm assuming. But I guess you could grow a liver in a dish if you wanted to. All right, Lane, you have a question. I'm waiting. And then we got to wrap this session up. This will be the perfect time for anyone else who has a question, right? Something you missed in the lab. You want to make sure you got a question correct, right? I know my setup was a little bit all over the place because I had to manage computer, chat, boiling stuff. That was a lot. Why do livers stop livering when alcohol is passed through over a long period of time, or why is there cancer? So two great questions. Well, alcohol can actually, it kills part of your liver, right? It's basically like your liver is abused essentially and it stops working. Now, the thing is your liver can to some degree regenerate, right? So it's only like long-term abuse over a really long period of time. Usually it depends on the person and the genetics and all other things. But your liver can sometimes recover from that stuff, sometimes not. But yeah, alcohol destroys it. And why is there cancer? We're going to talk about that later in the semester, so I'm not going to answer that one right now. We will actually review statistics again when we talk about cancer. But we're going to talk about cell cycle, right? And that's where cancer is involved. Because it's basically the cell going rogue and doing what it wants instead of doing what it's supposed to do. Okay, any other questions about livers, enzymes, this experiment, what you're supposed to do? Can somebody summarize for us what you're supposed to do now that this virtual session's over? Fill out the thingy. Great. The worksheet. Yeah, right? So this lab, you should be able to turn the entire lab in. Make sure you know the vocab, right? Make sure you answer the conclusion questions. Make sure you don't say, I was right, it worked, or some vague thing. Put some vocab in there. Practice using the vocab. There will be a question on the test that asks you how we proved oxygen was present in this experiment. So make sure you know how to do that. And if you try to explain it and you're not sure how to explain it, ask me because I'm going to grade the test. So there will be a question about that from this lab. Otherwise, the enzyme stuff is just going to help your understanding of science even more. All right. Well, that's all I've got for you guys. I see you're talking about a game about cancer, dragon cancer. Interesting. I didn't even know there was a game about cancer. All right. Well, I will see you guys next week. We will be doing a discussion-based assessment and reviewing this entire module. You can go check out those questions in advance. Otherwise, I will see you next week. So goodbye.